The last little bit of content we have in this chapter deals with enthalpy for reactions, so changing enthalpy for reactions. And there are some things that we should know about this. So for example, there are 3 basic rules on how these apply, and using some generic different kinds of reactions we can see this. So if a chemical reaction is multiplied by some factor, then the enthalpy for that reaction is multiplied by the same factor. All right, so what does that mean? So if I end up multiplying this by 2 for whatever reason, basically increasing the number of moles, like 2A's plus 2 times 2 is 4B's to make 2 times 1 is 2C's, then I have doubled the enthalpy that comes out of this. And that kind of makes sense. If I double the amount of everything going in, I should double the amount of energy that it takes, or the amount of energy coming out. So that's one thing that we should keep in mind. A second is that if a chemical reaction is reversed, then the delta H changes signs. So if I decide to run this reaction backwards, so C, instead of being my product, is now my reactant and becomes A and 2B, then whatever delta H was now, it's the opposite, so negative delta H. So if this was exothermic, now this is endothermic. Okay? And the last one is, if a chemical reaction is expressed as the sum of a series of steps, then delta H is the sum of all delta H for each step. That's probably a little difficult to just wrap your mind around in terms of words, so let's see what that actually looks like when we have it laid out. So here I've got delta H, and let me get the bottom page out of here so we're not, confusing ourselves. So I've got the delta H here for a couple of different reactions. A plus 2B goes to C, and C goes to 2D. And if I was going to add these 2 reactions together, because it's going to make a new net reaction, I can do that. But what I'll see here is I've got A plus 2B plus C, that's all my reactants, and that goes to make C plus 2D, that's all my products. I've got C on both sides here, so I can effectively cancel it out. So my overall reaction is A plus 2B goes to 2D, and my delta H for that reaction is the sum of these 2. So delta H1 plus delta H2. Okay, so however much energy it takes to do this reaction plus however much energy it takes to do this reaction is what I either need or get when this reaction goes. So, can we actually use that information? Well, yes, we can. So, diamond, which is one way that carbon exists, plus oxygen can make carbon dioxide, and when it does, it gives off 395.38 kilojoules. Graphite, another way that carbon can exist, when it combines with oxygen, makes carbon dioxide, and it will give us 393.5 kilojoules. Well, how much energy do we get or require when diamond turns into graphite? Well, if I want to sort of figure that out, I'm going to need to reverse one of these 2 reactions here. So I'm going to end up reversing this one. I'm going to turn this one around, make it CO2, and that becomes C graphite plus oxygen. Okay? So that when I add this first reaction to this one, certain things are going to cancel out. So for example, I've got O2 on both sides, I've got CO2 on both sides, and now I'm left with, when I add them up, and so my delta H, I probably shouldn't skip this step, becomes positive 393.5 kilojoules. So when I add them up, everything that's not crossed out here, so C diamond, goes to C graphite. And that's what I was asked to find. So negative 395.38 plus 393.5, that delta H of this reaction will end up being negative 1.88 kilojoules, which means that when diamonds turn into graphite, which they do quite readily, by the way, they end up giving off 1.88 kilojoules of energy. So it's energetically favorable for diamonds to turn into graphite. So for any of you that have a diamond, it's turning into graphite, just very, very slowly. So we can put that into a more robust kind of problem. So let's say that we're given these three equations here. C5H12 plus 8 oxygens goes to make 5 CO2s and 6 waters. Carbon plus oxygen makes CO2. 2 H2s plus O2 goes to make 2 H2O. And we want to use all of this information to figure out how much energy would be required or made when 5 moles of carbon and 6 moles of H2 go to make C6H12. So our main goal is to arrange these reactions so that they look like this one up here. Okay, so in this reaction, this is a reactant, and the one we're trying to make it's a product. So we're going to need to turn this one around for sure. Okay, in this reaction, a mole of carbon plus oxygen goes to make CO2. I need 5 moles of carbon here. And so I'm going to end up needing to multiply this one whole thing by 5. And then here I've got 2 moles of H2. Here I have 6, so I'm going to need to multiply this one by 3, which also means I need to reverse the sign on this one. I need to multiply this by 5, and I need to multiply this by 3 when I do it. So I'm just going to rewrite these just to be complete. So reversed, this would end up being 5 CO2 plus 6 H2O goes to make C5H12 plus 8 O2, and the delta H for that would have its sign reversed, so it becomes positive 3244.8 kilojoules. This one here is going to be multiplied by 5, so 5 carbons plus 5 O2s goes to make 5 CO2s, and my delta H for that, when I multiply this by 5, is negative 1967.5 kilojoules. And this one here, when I multiply everything by 3, well, this will become 6 H2s plus 3 O2s, going to make 6 H2Os. And my delta H for that will be 3 times this number, so negative 1450.5. Okay, so that's what I've done here. And if I add all these up, I can cancel out the things that are on both sides. So I've got 6 waters here, 6 waters cancels. I've got 8 O2s on this side, and I've got 5 and 3 making up 8 on this side, so those will cancel out. And if I've done this right, only the things that are in this top reaction here will be left over. I've still got some CO2s left, 5 on this side, 5 on the other side. So they're gone. So 5 carbons plus 6 H2s, that's all that's left on this side, going to make C5H12. That's exactly what I was being asked to make from up here. And my delta H for that is going to end up being the sum of these things, positive here, negative, and negative. And when I add those up, I get negative 173.2 kilojoules. So using the information from other reactions, I can figure out what the delta H for a new reaction is. And that's actually one of the really powerful aspects of this. It can be predictive, which is great. Well, that sums up everything we really wanted to do in this portion of chemistry. So make sure that you are trying out your homework and go back and review these if you're having any questions on any of the things that we covered. Thank you.